We share
theoretical and empirical reviews.
It is all about learning research facts and sharing with others.
Please subscribe to our channel if you like our videos.
Title of the paper: Dynamisms of Solar Radiation and Prescribed Heat Sources on Bidirectional Flow of Magnetized Eyring-Powell Nanofluid. Authors of the paper. Details of the paper. Before we present the theoretical review, let us consider a preliminary introduction.
Radiation is the thermal heat transfer carried out by electromagnetic waves. The concept of energy transfer through electromagnetic waves was introduced by Scottish scientist James Clerk Maxwell as the energy transmission that occurs at the speed of light. Ali, 2020.
According to some scholars, radiation heat transfer becomes important at high temperatures, that is above 1000 Kelvin. To some scholars and researchers, radiation heat transfer is the energy that is emitted by matter in the form of photons or electromagnetic waves.
This definition is true because all bodies including living entity radiate energy in the form of photons.
Radiation heat transfer plays a significant role in protecting the object inside the payload of rockets, the engine of a moving vehicle, and many industrial machines when the temperature at one part is much higher than that of the other side.
Radiation is one of the three modes of heat transfer independent of the intervening medium.
This phenomenon contradicts conduction and convection heat transfer that require a physical medium for energy to be transferred from one object to another.
The transfer of heat energy practically explains the propagation of particles from the hot region to the cold region. This is common in the cases of heat leakage and temperature control of satellites.
One of the outcomes of the experimental study by Pierre Prévost shows that indeed all bodies radiate heat energy either cold or hot. Poet Joseph Stephan in the year 1879 shows that total radiant heat energy can be measured, and this was adopted by Boltzmann Ludwig to form the fundamental basis of Stefan-Boltzmann law.
The Stefan-Boltzmann law of thermal radiation for a black body states that the rate of radiation energy from the surface per unit area is proportional to the fourth power of the temperature of the body.
Powell et al. 2010, remarked that
one radiative transfer is dependent on the equilibrium temperature between two objects of different quantities of heat energy. The radiative of a body depends on surface, composition, temperature, opacity, angle of interception or emission, and radiation wavelength.
2. In the absence of a medium, radiation is the only suitable mode of heat energy transfer. There exists a relationship between the vibrational, electronic, and rotational energy of molecules and atoms that form matter. These govern radiative emission and causes all objects to emit electromagnetic radiation.
3. Based on wave theory, the oscillation of waves during electromagnetic radiation is perpendicular to the direction of propagation. There exists a correlation between the strength of energy that will experience emission and the internal energy state of the emitter. Due to volumetric emission from every point, the strength of radiative energy increases as the propagation proceeds in a medium.
Consequently, radiation heat transfer is more efficient in a vacuum, and when the Prandtl number is small in magnitude. In such cases, there are no molecules or atoms, the radiation energy is not attenuated and, therefore, fully transmitted.
But for average viscous fluid and above, molecules and atoms can absorb, reflect, or transmit the radiation energy. The lack of an appropriate radiative heat transfer model leads to an incorrect simulation of the temperature distribution in the vessel.
However, the transmission of heat energy through electromagnetic waves has been modeled to be linear and recently as nonlinear. Nonlinear transmission of heat energy through electromagnetic waves was considered necessary and most suitable due to the significance of wall temperature during the process. Cordell, 2013. The source of the nonlinear heat transfer flux is not far-fetched. The nonlinearity can be simplified by using implicit differentiation to address the Ross-Eland approximation that models the radiative heat flux, since temperature differences within the flow are not always sufficiently small.
Hence, it is belittled and absurd to simplify the radiative heat flux by expanding T raised the power of 4 in a Taylor series expansion about free stream temperature, then neglecting higher order terms.
The concept of nonlinear thermal radiation was used by some scholars in the year 2018 to examine the effect of increasing thermal radiation parameter and the corresponding temperature parameter on the dynamics of the non-Newtonian Eyring-Powell fluid conveying alumina nanoparticles subject to thermal radiation.
The results show that the Nusselt number increases with thermal radiation at the rate of 0.015799606, while the temperature parameter increases the Nusselt number at the rate of 0.0067511067.
It is worth reporting that there exists a slight discrepancy in the observed results on the increase of thermal radiation in the literature. This can be associated with different definitions of the dimensionless parameter. In the literature, the two definitions are:
the effect of the radiation parameter is to reduce the temperature significantly in the flow region, page 1604, REF 6. Thermal radiation is the energy transfer by the emission of electromagnetic waves which carry heat energy away as the fluid flows.
Since the increase in radiation parameter means an increase in the rate at which heat energy is released from the flow region, this accounts for a decrease in temperature distribution as the magnitude of the thermal radiation parameter increases.
It is very important to remark that this effect depends on the definition of thermal radiation parameter.
In most published articles, if the thermal radiation parameter is defined otherwise, an increase in the parameter leads to an increase in the temperature distribution. Certainly, this is not realistic, that is, can temperature still increase when energy is transferred out of the fluid domain? Next, we shall now present the theoretical review.
Two-dimensional time-dependent Eyring-Powell liquid conveying tiny particles through a porous medium subject to Lorentz force and thermal radiation was examined with emphasis on a comparative analysis between predefined surface temperature and predefined heat flux. Next is to present the empirical review.
The analysis of Javed et al. 2020 shows that 1. Increasing thermal radiation leads to enhancement of the Nusselt number inversely proportional to the heat transfer at the lower rate of 0.331928966 when temperature parameter is small, and larger rate of 0.608038276 when temperature parameter is large.
2. Increasing thermal radiation was discovered to be a factor capable to diminish the Sherwood number, which is a quantity proportional to the mass transfer. More so, a higher decreasing rate of Sherwood number due to a growth in the thermal radiation is ascertained when the temperature parameter is sufficiently large.
3. A significant variation in heat energy is achievable when predefined heat flux was used compared to the case of predefined surface temperature. Acknowledgements.
Special thanks to all the editors and reviewers of case studies in thermal engineering, Elsevier Publishing. We share appreciates the contribution of the authors to the body of knowledge.